Good day. Today we are going to discuss some problems related to kinematics of a particle. Okay, so let's solve example number 1. The motion of a particle is defined by the relation x is equal to 6t raised to 4 minus 2t cubed minus 12t squared plus 3t plus 3, where x and t are expressed in meters and seconds respectively. Determine the time, position, and velocity when a is equal to 0. So from the problem, we are given the equation of position, and from here, we are going to solve now for the time t, position x, and the velocity v at a, which is your acceleration, equivalent to 0. So as we have defined in our introduction and from your physics, we have learned that the velocity is a derivative of the position. Thus, v is equal to dx over dt. So from our given equation x, the derivative now is equal to 24t cubed minus 6t squared minus 24t plus 3. Likewise, the acceleration is the derivative of the velocity, which is a equal to dv over dt. So from our derived equation of the velocity, we again derive this equation, giving us a value 72 t squared minus 12t minus 24. So since we want to solve for our values at an acceleration equal to 0, so we start off first with the first, or the equation of acceleration. So we equate this to 0. We can simplify the given equation by dividing it by 12. So we'll have a simplified form of 6t squared minus t minus 2 equal to 0. So given this equation, we can solve now for the values of t by quadratic equation or by computing for our roots. So for the roots now, we can solve it as 3t minus 2 times 2t plus 1. So from here, we can now take the first root of t is equal to 2/3 seconds, and the second root of time is equal to negative 1/2 second. So there is no negative time. So what will govern is the first value of t, which is 2/3 seconds. So since we want to solve for the position and velocity as well at a equal to 0, that is at a time equal to 2/3 seconds. So what we will do is to simply substitute now the value of t in our equation of velocity and position. So let's start with the velocity first. So substituting the value of 2/3 in the equation, we will get a velocity equal to negative 8.556 meters per second. And substituting the time t equal to 2/3 in the equation of position, we will now get a value of x equal to 0.259 meters. So example number 2. The acceleration of a particle is directly proportional to the time t. At time equal to 0, the velocity of the particle is given at 0.4 meters per second. Knowing that v is equivalent to 0.38 meters per second and that x is equal to 0.5 meters when t is equal to 1 second, determine the velocity, the position, and total distance traveled when t is equal to 7 seconds. So our given are the proportionality of acceleration to the time. So we could write it in an equation wherein a is equal now to k times t, where k is a constant value. We're also given that at time equal to 0, the velocity of the particle is 0.4 meters per second. And also, we're given at time equal to 1 second, the velocity and the position is at 0.38 meters per second and 0.5 meters respectively. So we want to solve now for the total distance traveled when t is equal to 7 seconds and the velocity and position at this time. So for our solution, we have identified the equation of acceleration as a function of time, and we also know that acceleration is the derivative of the velocity with respect to time. So we now have dv is equal to a dt. Substituting now the equation of a as a function of time in this equation and getting the integral of the equation, we now have the integral of dv from vo to v is equal to a dt from 0 to time, or that's also equivalent to kt dt. So if we're going to get now the integral, will now have v from 0.4 to a certain velocity is equal to k times t squared all over 2 from 0 to t seconds. So we could rewrite the equation as v minus 0.4 is equal to kt squared divided by 2. So we now solve for the value of k, and we use the given t is equal to 1 second and v is equal to 0.38 meters per second. So with this, substitute the value of v in our equation. We'll now have 0.38 minus 0.4 is equal to k times 1 squared divided by 2, or that will now be equivalent to k equal to negative 0.04. So substituting the value of k in the equation of v, then our general equation now for the velocity is equal to 0.4 minus 0.02 t squared. So next, we know that the velocity is the derivative of x with respect to time. So we can write now dx is equal to v dt. So taking now the integral of the equation, we'll now have dx from x1 to x2 is equal to the value or the equation of the velocity which we have just derived in the previous slide, dt from t1 to t2. So we'll follow at t1 is equal to 1 second and x1 is 0.5 meters. So we could now write x2 minus 0.5, which is the simplified integral of dx, is equal to 0.4 t minus 0.02 t cubed divided by 3. And that is from 1 second to t2. Substituting now the value of t2 and 1 in our equation, we'll now arrive at a general equation of x, which is 0.107 plus 0.40 minus 0.02 t cubed divided by 3. So we have computed or derived the equations for velocity and the position. So we can now solve for their values when time is equal to 7 seconds. So we'll just simply substitute 7 seconds in our equation of velocity. So that will now give us a value of negative 0.58 meters per second. And the same, we substitute 7 seconds to the equation of the position. So we'll arrive at x at 7 seconds is equal to 0.620 meters. So solving for the total distance traveled of the particle when the time is equal to 7 seconds, we solve for the location or the position of the particle when time is equal to 0 or it is at its start. So we substitute 0 in the equation of position, thus arriving at a value of 0.107 meters. If you could remember, we have computed a negative velocity when our particle is at 7 seconds. So there's a possibility that our particle has moved back going to the original point. So in that case, we'll now solve for the time when the velocity is equal to 0. So we'll now have the equation 0, or the velocity, is equal to 0.4 minus 0.02 t squared, giving us a value of 4.472 seconds. And at the same time, we'll solve for the position of the particle during this time. So we'll have now substitute time in the position equation, giving us a value of x equal to 1.3 meters. So what does it mean? So if this is the line of motion of the particle, so we have this point as x equal to 0. So at time equivalent to 0, the position of the particle is at 0.107 meters from your reference point. And then at 7 seconds, we have computed that its position is at 6.20 meters. And at 4.472 seconds, its position is at 1.3 meters. So as you can see, the particle now has moved from 0 to 4.472. Pero hindi pa niya naabot yung 7 seconds. So yung 7 seconds nandoon sa pagitan ng 0 na time saka ng 0 na velocity. So it means that the particle moved back towards the origin from 4.472. So meaning, for the distance traveled by the particle within 7 seconds, that will now be computed through 0 to 4.472 to 7 seconds. So with that, we'll now compute for the distance first from 0 seconds to 0 velocity, or that's 4.472 seconds. So that will now be 1.3 minus 0.107, or the distance to travel to the positive direction is 1.193 meters. And then, from stopping, going to 7 seconds, we compute for the distance traveled, so that will be 0.62 minus 1.3, which is negative 0.68. So do remember that for distances, we use the absolute value. So meaning the total distance now is computed as the total absolute value of the displacement. So total distance is equal now to 1.193 plus 0.68, which is equal to 1.873 meters.